Let's get started. You can stop working on it. It's incredibly unlikely to find the optimal solution in the time that I gave you and the resources that you have, being a pencil and paper. So don't worry about it. We'll talk about it in like literally 2 minutes. So we'll come back to it in just a moment. Okay, so today we are finally moving away from stat solving. So past 4 weeks, that's pretty much all we've been talking about. But again, like hopefully by now we recognize it's an important problem, it has a lot of foundations, and we can solve a lot of other problems if we can solve SAT. So today we'll start looking at some high-level solvers. So the way you can think about this is like, whereas with SAT we were working very closely with the literals and clauses and like building clauses to encode constraints of problems. Here we'll look at some more mathematical formulations of constraints. So it should be a little bit more comfortable, hopefully. Okay. Just some reminders before we get into stuff. Homework 2 was released a few days ago, and it will be due on Monday, the 7th at 11:59 p.m. It is encouraged to start early, especially because setup isn't really the right term, but there's just some issues with like it has to run with certain versions of Python, and like since then I've like updated the homework to hopefully run with all versions of Python, but it's still good to like at least start early and make sure everything's running smoothly. If not, post on ed and we'll take care of it. But it is one of the longer assignments. It's probably the longest assignment out of all of them, so start early. Also, I believe fall break is next week. The Thursday is the first day. And I put no class with a question mark next to it because, we have class on Thursday and Thursday's fall break. But I don't know, is there like some sort of different schedule next week where it's like Thursday, Friday schedule and Tuesday, Wednesday?
Different schedule for Thanksgiving break.
For Thanksgiving break.
Yeah, so that will be a Thursday, Friday schedule. But also I think a lot of people will start traveling earlier.
Okay, well, we'll see. Okay, if there's no schedule change next week, then no class next week. Excellent. Cool. Anything before we get into stuff? Questions? Okay, this is the question that I gave you guys. Like I said, kind of infeasible to come up with an optimal solution given the time and resources you had, but yeah, I just want to see what groups came up with, and we can see who came up with the best solution. So, your group, Alex LaRouche?
We didn't really get anywhere.
No?
But I think one thing we're talking about is maybe there's like one optimal ingredient, and we just try to like spend all our money there.
Get a lot of that?
Yeah.
Okay, that's a good idea. Ishaan, your group?
The first thing we looked at was like the brand for buck in terms of like how many like calories you're getting per like dollar you spend. So for the highest amount was for couscous, which we were getting like 740.74. But we realized that like if we buy all of couscous, we go above the sodium limit.
Mm-hmm.
So then we sort of like just set up because you have the sodium and calories thing, and you know that because you're not bound to integers, your most optimal meal will I think have exactly 5,000 calories.
Okay.
Or exactly 200 milligrams of sodium, at least one of them.
Sure.
So we're sort of setting up like simultaneous equations like that, but that only eliminates one variable, so I don't know what you can do.
So did you come up with like any sort of potential solution?
Not solution, but bound. Like 30 times the rice plus 37 times the pasta should be 100 if you set both bounds to 100, but I don't know if that's accurate.
Okay. And then, Engineer Thomas, your group?
Yeah, we had a similar approach to the first group where like we wanted to isolate one item. We were like rice because it's like the cheapest per kilogram.
Mm-hmm.
But then I guess the first thing we did was we wrote down the two inequality equations and the equation for the price, and then just simplified the constants and the coefficients. And I guess what we got was like kind of good was like R equal like 11 kilograms of rice and then 1 kilogram of pasta. Now we came about it, I came about it in a stupid way because I thought it was greater than equal to 40, so I said, sorry. The lower bound, you want it to be less than equal to 200 milligrams, and I for some reason wrote down greater than equal to 200.
Okay.
So I said that, but it ended up being okay because it still meets the calorie requirement just barely.
Cool. Okay. Good. Yeah, I mean, hopefully you can tell, kind of a challenging problem to do by hand, but this gives inspiration for what we'll talk about today. So, okay, I can give it to you now. The solution is not here. We'll see in a little bit. Yes, we will see it in a little bit. I won't spoil it yet. Okay. So the thing we'll talk about for the majority of today is something called linear programming. And the idea of linear programming is dealing with a bunch of like mathematical functions at the same time. So when we talked about SAT was a decision problem. Given a formula, we said yes or no. It can be satisfied or it can't be satisfied. When we talk about linear programming, this is going to be an optimization problem, where we're looking to find the best of something, maximize something or minimize something. So you guys were dealing with a problem where you had to minimize cost. It's going to fall into the realm of linear programming. So we'll define all of our stuff just to build up what linear programming looks like and then dive into it. So for a bit of terminology, mathematics, a linear function on n variables looks something like this. It is a linear combination. It is the variables with exponent 1 with some sort of associated real number coefficient, all of them added together plus a constant. Just a linear function. So, an example of one could be like 3x1 plus 5x2 plus 7. That's an example of a linear function. So there's no quadratic terms or anything like that, just everything has power 1. And a linear inequality is kind of what it sounds like. On the one side, you have a linear function. Now it's bounded by some constant, greater than or equal to b, less than or equal to b. So anytime we say linear function, this is the type of thing we'll look at. And if you're linear algebra inclined, which I'm not, you can just think about this as like the product of two matrices, A being like a row vector of coefficients, and X being like your column vector of variables. And it's just essentially like taking the dot product of the two or multiplying them however you want. So linear algebra, linear function. I don't like linear algebra, so we're not talking about that today. So yeah, like I mentioned, linear programming deals with optimization, finding the best or worst of something, maximizing something or minimizing something. And we're dealing with linear functions. We're aiming to optimize a linear function. However, we'll have constraints given by linear inequalities. And maybe you're picking up on the warm-up exercise where we're minimizing like the price, which was a function of the foods that we had, but at the same time we had these constraints that it had to be at most 5,000 calories and at least 200 milligrams of sodium. So that's sort of what we're getting at here. And interestingly, like this type of problem, linear programming, shows up in a lot of different places. Anywhere from like just, I don't know, as simple as like maximizing values of functions to like decision making, machine learning. So this appears a lot, and it's universally asked for. So that's why this is so important. Cool. So this is an example linear program. LP stands for linear program. So if I say LP, which I will be, that's what I'm referring to. And this is like a formalization of it, where we're minimizing some function subject to some constraints. Now, if we look at this example in particular, this one we can kind of solve by hand. Like we can kind of argue a solution ourselves that, if we're minimizing the function, if I look at my first variable x1, I kind of want this to be as small as possible. Because if I make x1 large, and I'm multiplying it by 3 and adding it to my function, the overall thing is just going to grow larger and larger. So maybe I want x1 as small as possible. And in this case, my constraints say that x1 has to be at least 0, but it also has to be at least 2. So it seems quite logical to say, okay, why don't we just say x1 equals 2? Right? Because if I put 2 in, it contributes 6 to my function. If I put 3, now it's contributing 9. Reasonable? Yeah, okay. What can we intuit about variables x2 and x3, Rush?
Yeah, so since like x3 is being like subtracted, we want to maximize x3. And so like since we know that x2 plus 2x, and we also want to minimize x2 because it's contributing positive to the end result. So with the x2 plus 2x3 constraint, like since we want to maximize x3 and minimize x2, we just say that x3 is 5 and x2 is 0.
Perfect. Makes sense to everyone? You know, we want x3 to be very large and x2 to be very small for similar reasons. Working with the constraints, that's the largest we can make x3 while keeping x2 as small as possible. And that's the solution. Good job. Like we solved this one by hand. Here's another LP. Yeah, this one's a lot harder to solve by hand. And the reason is, like, if you start intuiting things like, okay, you know, I want x1 and x2 to be very large because they're contributing positively. So maybe I set both of them to 3. Then I start looking at my constraints and, you know, if I set both of them to 3, this third constraint, x1 plus 2x2, will not be less than or equal to 7. So then you have to change that up, and it's going to be quite messy. However, we're going to take some time to build up to a solution on our own. Like, even though it initially seems very hard to work with our hands, we'll still do the best that we can. So, let's erase this. Any questions thus far before we explain how we could solve this? Okay. We have two variables. They can take on like real numbers. So let's just imagine some sort of like coordinate plane. So your horizontal axis will be values of x1, your vertical axis will be values of x2. So if I choose a point in my plane, you know, maybe this is like 7 comma pi over 2. This is something we could test out, right? Like, it gives me a value for x1 and a value for x2. Just dealing with the variables on their own. Now we would want to like impose our constraints. And the idea is like we're going to try to section off a part of our plane which contains all of the feasible points. Points that we could test out such that their values of x1 and x2 will abide to all of these constraints at once. So we're just figuring out what part of this plane we can look at. And we can do this just by graphing our constraints. So like the first one says that x1 and x2 both must be in between 0 and 3. So if I, stupid marker, I can, that's also kind of bad, but whatever. This is at 3, and then maybe we have the other one at 3. So just by the first constraint, any point I choose within this square will abide to the first constraint. Agreed? Cool. Okay. Now let's do the second constraint. So yeah, it's been a while since I've graphed something. So let's see. Minus 2x1 plus 2x2 is less than or equal to 5. What does this look like? Is that right?
Yeah.
Yeah? Okay, I'm not making any mistakes. So the intercept is at 2.5. Reasonable? Makes sense? Yeah? And it's saying, okay, our things have to be below this line. It's less than or equal to. So we've cut off a corner of our square. But still, anything that falls within this region will now abide to the first two constraints. Okay, let's do the third one. x1 plus, 2x2 less than or equal to 7. So x2 less than or equal to negative 1/2 x1 plus 7/2. No mistakes? Okay, good. 7/2 is up here, and my slope is negative 1/2, so I should intersect like there. Wait, no, like here. Close enough, right? Kind of close, whatever. I'm not an artist. Last one, 2x1 plus x2 less than or equal to 7. So x2 less than or equal to negative 2x1 plus 7. Oh, gosh, okay. So it's up here somewhere. Where does it intersect the x-axis?
I don't think it's going to intercept the
3,
square,
1.
though, right?
Where?
Yeah.
What?
It intersects at 3, 1.
3, 1. So like here?
Yeah.
And at 2, 3.
2, 3. So like here. Yeah? Do you have a ruler?
I'm surprised he lives in Desmos.
Well, if you look at the lecture notes, there will be a drawing in Desmos. Okay, those are all of our constraints. We've cut off our square, and it's saying anything within, oh my god. Oh, I feel like this is a weekly occurrence now. Oh, this is also blue. Oh, there we go. Okay, like anything within this region abides to all of the constraints, because we just graphed it, and we're, the inequalities point in which direction. In this case, they were all saying less than or equal to below it. So we're going to call this region the feasible region. Any point I select in my feasible region could be a potential solution. I don't have to worry about it breaking any of the constraints. Now the thing is, we still want to maximize some function. And any one of these points are candidates. So sure, we can just test out all of these points, but that would require us testing out all of these points and figuring out which one maximizes the function. It turns out there is an absolutely brilliant observation that can be made. And the observation is that our solution, the point that maximizes this function, must occur at one of the corners of this feasible region. So either here, there, 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 there. So if this claim, whatever I'm saying, that it must be one of these points that solves it, if that's true, well, then we only have to test 7 points instead of an infinite amount of points. But why would it be true? Why would our solution be at a corner?
Like the way I think about it is that like if the corner points represent like the intersection points of like 2 of our constraints, and that sort of means like those 2 constraints are like stretched out, so like they're pushed to like as much as we can take them. And then if we check like pairwise every however much we can push any pairs of the constraints, then one of them has to be the maximal or like the minimal answer.
Sure.
I think first, like the most intuitive thing is that within the feasible region, it's going to be somewhere along the boundary. Because if it's within the feasible region, that means like you're just not pushing it towards any one side. And then arguing why you're going from like a boundary to a specific corner, if like the argument is that if it was anywhere on any edge, like similar to what Madhav said, if you're on an edge, then like moving either way, like towards either of the 2 corners is gonna like be beneficial or worse.
Yeah, you guys have the right intuition. And so like, we can prove this, and it's like a slightly ugly proof, not like ugly in that it's hard, but like you can just take the gradient of your function and like do a whole bunch of stuff that way with math. But I personally think like providing a verbal explanation might be less rigorous, but it might make more sense. So the way I'll try to explain it is as follows. We had this feasible region, and what we would do to find a solution is choose a point and plug it into that function. We would just choose points and plug it in and figure out which one is the maximum. Instead of viewing this as like a flat region of points that we're just selecting from, instead imagine this as a mountain, where each point in my feasible region also has an elevation associated to it. So you can climb this feasible region and you're up some amount into the air. But that elevation will be given by our function. So you can imagine you're traversing a mountain. Now the goal is to find the peak of the mountain. Where's the highest point? Because that would be maximizing this function. The key thing to note here is that our function is linear. It's, in this case, a function of two variables. So when we look at the slope of the function, or like how it's changing, it's a constant change. It's going to be this flat increase of a mountain because graphing this out, you just have a plane that you're dealing with. So you're on some mountain that like basically only goes up and there's no bumpiness to it or whatever. You're just walking up a straight incline in some direction. So maybe you start here, and you're clearly not at the peak, because if you climb uphill, you'll get higher and higher up the mountain, which is what you want. So maybe you just follow that direction of the arrow, and eventually you get to an edge. From here, you can claim that at least one of these 2 points should be at an elevation at least equal to where you're at, if not higher. A simple proof for this is like, if they were both below you, that means you're at like a local maxima, but we're dealing with a linear function or like a plane, so that can't quite happen. But like another way of thinking about it is like, okay, maybe this arrow is bad. Maybe you do an arrow like this, that's also kind of bad. Like this, and you climb up to here. What you can imagine is sort of like taking this region, rotating it so that with the arrows pointing up, and figure out what's the topmost point, and it will always be a corner. So like this last part is a little bit hand wavy here. I think the argument of like if the corners are below you, then it's a maxima. That's like a nice argument. But yeah, think of it as like climbing a mountain that has this steady increasing slope. Kind of makes sense? Clear? So this is pretty massive, right? Like we've cut down a huge region to just a few points, and we would just test those out and figure out which one is maximum. So it turns out that LP, linear programming, is polytime solvable. So solutions exist that run in polynomial time, which is fantastic, right? And this seemed like a pretty hard problem, but it can be solved in polynomial time. And the algorithm that's used in practice is called the simplex algorithm. And it essentially does what we just did. Kind of creates this feasible region and then traverses all of its points and tests it out. Like all of the corners. One very important thing to note is that this example was very nice. Because I could draw it out. We had 2 variables. I could draw out a plane and then lines cutting it off. But if we had 3 variables or 4 variables, then we need 3 or 4 axes, and then we're dealing with like hyperspace, and it's much harder to visualize how we're cutting things. So not all of the problems are just going to be these 2 variables, which is why I'll bring it to this point that this algorithm, it actually has worst case exponential time, the simplex algorithm, though we still choose to use it, even though it's not polynomial time solvable. We use it because for most instances, it's pretty fast, and it works. This was developed in 1947. There's a pretty fascinating story behind it, but I forgot most of it. To my recollection, there's like this dude, George, and I think he was working for like the army or military during some war, and his like coworkers or colleagues recognized that he was really smart, And one of the coworkers was afraid that he was going to leave because he got bored of the work. So the coworker was like, oh, here's a problem, try to solve it. And it turns out it was like some sort of linear programming problem. And then this dude, George, created this method. So pretty fascinating how it came out to be. You can read up on like Wikipedia, but yeah, I thought it was pretty fun.
I'm a bit confused. Like on the previous slide, like we also said that LP is polynomial time solvable. So like, is the problem itself like polynomial time solvable, or is it just the algorithm that's exponential in this case?
So
Is it polynomial time algorithm?
the class of linear programming problems, like any instance of a linear program, can be solved in polynomial time. It's just that this first algorithm that they came up with happens to run in exponential time. But like in 1984, like this new algorithm came out called Carmarker's algorithm. This actually ran in polynomial time, and it's like actually fast. So I think switched to using this. The details of how this works is a bit too complex, but like from my understanding, it's a similar idea where you create the feasible region. Now you just choose a point inside and kind of like smartly crawl your way up to a corner. A bit too complex for this. It would require a whole separate lecture, so we won't go into it. But yeah, like by 1984, we had this polynomial time algorithm.
He was 28 years old.
28?
Yeah, it says there.
Unbelievable. Okay. Any questions thus far? Yeah, don't just think that like, oh, we graph this, it's easy. Like, the minute we add more variables and more constraints, it gets harder for us to imagine things. So let's try to create and solve a linear program. So surprise, surprise, this question is just an instance of a linear program, though it's, in disguise. So yeah, like together we're going to transform this problem into an instance of a linear program where we like maximize or minimize something subject to some constraints. So before we do all that, there are like three main things you want to do for any linear program. Three things that you want to do or define. So first would be like define your variables. What are your like x1, x2, x3? Number two would be to write the objective function. So this is the linear function that you want to maximize or minimize. And lastly is to write the constraints. Yeah, so those are like the three main things. So we're going to transform this question into a linear program. So first thing we have to do is define the variables. And how do you figure out what the variables are? A good question you can ask yourself is like, what are the things that are changing? Which, that is what a variable does, but like, what are the things that we have the ability to change or can change throughout a problem?
Yeah, so like the amount of each item, so like you have a variable corresponding to like the amount of rice, pasta, and couscous that you have.
Yeah, like we'll just have R, P, and C, which is exactly as you said, amount of whatever it is, rice. That's like what we have to change. Those are our three variables. Good, that's done. What's the objective function? What are we looking to maximize or minimize? Doesn't have to be in terms of math, just in general. Yeah.
1.25R plus 1.65B plus 1.25C.
So what does that give us?
You want to minimize the price.
Oh, minimize, yeah.
You want to minimize that function.
Right. We're looking to minimize price, and we can write price as a function of our variables. Can you just say it again for me? Sorry.
1.25R plus 1.65B plus 1.35C.
Cool. Yeah, with the variables that Arush provided us, with Ishaan's equation, plugging in values for that would give us the price, and we're looking to minimize it. And great, that's a linear equation, exactly what we wanted. Good, so that's step 2 done. Next, we want to do the constraints. So, yeah, what are our constraints?
So I can do the first one. So for the greater than or equal to 5,000 calories, you could just say that 750 R plus 1200 P plus 1000 C has to be greater than or equal to 5,000.
Awesome. Similar to what we did for price, just now for calories. And then the last one I'll do, which is sodium. So this would be 15R plus, 35P plus 60C has to be less than or equal to 200. Fair enough? Any other constraints? Yeah.
RBC greater than or equal to 0.
Perfect. Yeah, it's something we kind of took for granted or implicitly assumed that like we have to buy, or we can't buy a negative amount of the items, but we haven't encoded that in our problem yet. So yeah, those are all of the constraints now. And we can find a solution to it. In fact, let's do that now. So let me make sure everything's working here. That's visible. Okay, I'll type a little bit and then I'll explain. So, this file and other files will be posted on the website, so don't worry about like coding it yourselves. You can just watch. So, the thing that we're going to be using, the library we're going to use is OR tools. This is a library published by Google. OR stands for Operations Research, and it solves a whole bunch of different things. We are dealing with linear programming, so we're importing the linear solver, and then just a wrapper to Python. So that's just the first line. Is this visible, or do we need it a little bit larger? Good. I'll just do one click more, just for peace of mind. Okay, so we're going to use this solver to solve a linear program. Good, that's still there. So first thing that I'll do is actually like define what my solver is. So this, I'm going to give it 2 parameters versus just telling it what kind of solver, in this case, a basic linear program. And then I also need to give it this second parameter, which is the solver itself. You can see linear programming is in there, so we're probably in a good place. glop is Google linear something programming, I don't know. But that's the solver we're going to use. Just know that solves linear programs. And using this solver, we can give it variables, we can give it an equation to maximize or minimize, we can give it constraints, and it will output something. So we're going to do that right now. So as we did, the first step was define our variables. So we had R, P, and C. The way we're going to define variables is called a solver. We're going to say R is going to be a numerical value. We'll provide a lower bound, 0, and an upper bound. In our formulation, we don't really have an upper bound, so we're going to say it's going to be infinity. And then lastly, we'll give it a name, R. We'll do the same thing for P and the same thing for C. I'll just copy this, that, give it different names. Cool. Variables are defined, lower and upper bound. Now, we'll kind of go out of order. We'll do step 3 next, which is give it constraints. So there are a couple of ways we can define the constraints. One way is to just simply write out the expression that is a constraint. So like the calories constraint said, it's a function that's 750 times R plus 1200 times P plus 1000 times C. And the constraint itself that we have is that these calories, whatever value we get out of it, has to be at least 5,000. So calorie constraint is going to be evaluated to either true or false, depending on what our function outputs. And then we can go ahead and add it to the solver, just solver.add. Another way of doing it is a lot simpler, and we'll do this with the second constraint right there, where we just go ahead and say solver.add and write out the constraint. I think that's a little bit easier, but everyone has their own choice. And then there's the third constraint. But I'm not going to code this because, part of defining these numbers was giving it a lower bound. So I just took the third constraint and put it into the solver like this. So I don't need to add that as another constraint. Cool. And then now we'll give it the objective function. So step 2, I guess, give the objective function. So we are looking to minimize a function, and you can expect there to be a maximize, so that works too. And again, give it the function that we want to minimize. So like if you look at whatever we just did, it's like exactly what we did right here. R, P, and C, we define them, give the constraints over there. It's just a bunch of solver.adds. And then we'll run the solver, but I just want to format some things first, and then we'll look at it. So if we get the optimal solution, we're going to print a very ugly f string. So this is just saying, like, when I get my optimal solution, let me print out what the values of R, P, and C are. R, P, and C, yeah. And I don't feel like printing out the other thing. And if not, we'll just print not possible. Okay, so that's the entirety of the program. Let's see what happens when we run it. It's because it's a new virtual environment. Okay, that's our solution. 0 rices, 2.7 pastas, and 1.7 couscouses.
Just as an aside question, is there any way of copying virtual environments in Python, like creating a copy? Like if you have like one, and then you want to like use the same like dependencies, can you just like create a copy of it or no?
Does anyone know? I'm pretty bad at this stuff.
So all of this stuff is cached anyways. So you should create a new virtual environment for every project, but like stuff like NumPy, Pandas will all be instant when you install it because it's already cached in some local.
So you can just push the command.
Yeah, you would just like pip3 install it, or in this class we use Poetry, so just Poetry.
Thanks.
Cool. Oh, no, thank you. Yeah, I mean, so this just outputted the solution. It's a little bit different from your solution, guys. That's all right. So yeah, the amount of calories that this gives is like, well, let me see if I can print it out. Calories. And we're going to print out, we had this function here above called calories. Calories.solution value. And
do the sodium as well.
Sure. Let's see. Where is sodium here? Sodium equals 15 times R plus 35 times P plus 60 times C. And let's print that out here. Copy, paste, sodium. What are our guesses as to what these values might be?
One of them has to be at the boundary.
Okay, so maybe calories is at 5,000 or calories at 200.
Maybe because you have like real value and not integer values, both of them could be at the boundary. I don't know.
Maybe. Any other guesses? I mean, we're about to find out. I don't really know, so let's see.
Yeah.
Both of them are at the boundary. Pretty cool. Yeah.
If
So.
you change it to integer, then like both of them will like start guessing, I guess, like, as close as they can get. But since it's like real value, like it makes sense.
Right. Cool. So yeah, I mean, that's just like how you would solve LPs with OR tools. Questions on the demo? Yeah, okay. The file will be posted, so we can look at it at your own time. Oh boy, time is a ticking. So this is just exactly what we did. That's the equations we came up with. Hooray. Where am I in my notes? goodness, I'm so lost. Oh, what? Page 5, page 4. Ah, okay, here we go. Did that. Okay, let's see a new problem. So, yeah, this is a new problem that we're going to explore, and it's going to dive into the world of LP as well. We'll see how they relate. So we're going to deal with the max flows problem. If you've taken CIS1921, you probably spent like 17 lectures on this, give or take. If not, that's okay. We're going to talk about it right now. So the max flow problem says we have a directed graph. We have a source, which we'll call S, and we have a sink, which we'll call T. And all of our edges have capacities. So in this drawing, it's the second number, whatever comes second. And that's saying, like, I can only hold at most that many units of flow on my edge. So this edge can only hold at most 3 units. And the problem is saying, okay, starting from S, we're going to send out units of flow, or you can think about it as like pouring water, such that, and it goes along these edges, such that whatever water goes into a vertex must leave that vertex. So as an example, for R, this is saying 2 units of flow out of the 2 possible will enter R, and this has 1 unit of flow. So it has to have 3 units of flow exiting it, which it can through this edge, since its capacity is 3. The question asks, what's the maximum amount of flow that can be sent out? So in this case, the answer is 5. Just 2 plus 3 is 5. That's the question we'll deal with. Any questions regarding the flow question? Because it might be unfamiliar to some people.
Can you explain it again?
Yes. Directed graph,
Yeah.
source, sink.
Yeah.
Edges have capacity. Saying like, we'll say this one has capacity 2. So I'm going to put stuff on my edges, and I can't have more than 2 stuff on it. Like I can only hold 2 items. So starting from here, I'm going to send out units of stuff, units of water, and the amount that I send out along the edges can't exceed its capacity.
But we're free to choose like how we want to split it, right? Like,
Sure, yeah.
The constraint is that how much ever goes into one internal node has to exit.
Whatever goes into a node has to leave, and nothing can disappear.
Yeah.
Conservation of flow,
Yeah.
that's what it's called. And what's the most amount of flow we can send out from S?
Oh, like only from the sink. Like what's the most amount?
From the source, yeah. How much can we send
Source,
out?
okay.
Yeah. So in this case,
equal the amount that reaches the target, of course.
exactly, yeah. Everything that comes out must go in. Flow
There's
question
only,
makes
like,
sense?
One like source and one target.
Yeah. Let's just say that for now. Make sense to people? Okay. This question is well known, and it's solved in polynomial time. There's an algorithm called, there's Ford-Fulkerson, there's Edmonds-Karp. Edmonds-Karp runs in time, what is it, like O of VE squared, where V is the vertex set, E is the edge set. Well-known problem, polynomial time solvable. We're going to transform it into an LP. Why would we ever want to do this? Well, you can think back to a very early lecture where we talked about the stable matching problem, and we encoded it as SAT, and even though stable matching was polynomial time solvable, we said, maybe it's nice to have it as SAT, because once we consider deviations of the problem, it may become NP complete. So, maybe that's a similar justification. So, we'll do the same procedure. Define the variables, write the objective function, write the constraint. So we'll start with the variables. What is changing? What do we have the ability to change, or what are we observing could be changing in our problem?
I think like one way of defining the variables could be the number of units you're sending along any edge. So that has a constraint as well, which is like the max capacity of that edge, and then.
Yeah, no, exactly what you said. Our variables will be the flow along each edge. Each edge will have its own flow, because that amount could change. Very good. What is our objective? Doesn't have to be in terms of the variables, but it could be if you want it to be.
Maximize the flow from the out edges of the source.
Beautiful. That's exactly what Arush said, just in terms of math. That for each vertex set, or for each vertex in the out set of our source, we will sum together its flow. So like, I don't know, we have S here, and it has a bunch of edges going out to these vertices, sum the flow along those three edges. That's all that's saying. Another way of viewing this is by actually considering a new edge that we add to the graph. So what the other formulation is saying is that suppose we add an edge from T pointing to S that has infinite capacity. So when we send the flow, we'll get 5 units of flow here, and that's just going to go back to S because we've added this new edge. And another way of writing the objective is just like maximize the flow along that edge. That kind of makes sense. Just an infinite capacity edge going back to the source. That may be helpful, not now, but maybe later. I don't know. Okay, and then there are a couple of constraints that we kind of hinted at. First is the capacity constraint, that the amount of flow on an edge shouldn't exceed the capacity of the edge. Okay, I'll just give you that one. It's hard to explain. It's like, that's a variable that we created. These capacities are given to you because that's part of the problem. So the amount of flow must be less than or equal to the capacity, but it also has to be non-negative. So that's the constraint we would have. What about conservation? That the amount of flow that enters a vertex must be the amount that exits it. Any ideas on how we can do that? Ishaan?
For all vertex, for all vertices V, the sum of f u v for all u is equal to the sum of f v t for all t.
Yeah, I think you pretty much got it, but just visualize this here. Let's call this V. So the vertices that point into V, we'll call this the neighbor inset of V, and everything that comes out of it, as before, is the neighbor outset of V. And so the sum of the flow along these edges should equal the sum of the flow out of these edges. So summing over all vertices in the inset, shouldn't use V, U. We'll take the flow along that edge, so f of u v should equal the sum over all vertices in the outset of f of v u. Cool. So this is essentially saying that. It's just a different formulation, that the difference of these sums equals 0. It's just taking this sum, or this equality, moving one sum to the other side, subtracting it. Same exact thing. And we would define this for all vertices that are not S or T. Okay. Yeah, so that's like fully defining the LP. We have the objective function, variables, and constraints. Let's see, what's after this? Oh, it is a demo. Okay, I'm not going to code all of it because we don't have that much time, and honestly, it would be kind of boring. So I'll just briefly scroll through it, and you can look at it on your own time. The way this works is we have a flow network, which is your vertex, what it points to, as well as its capacity, defined as this, whatever, dictionary, I don't know. And again, we're using this glop linear programming, calling it max flows, and basically the same thing as before. First, you define all of your variables. And in this case, we are looping through the vertices of our flow network and considering what are its neighbors, and that creates a vertex. And then we go ahead and do our constraints. So this is doing the the conservation constraint here, where, you check the neighbors and then add to the sum, and in the end, hopefully they're equal to each other. And then, what's the other constraint? Oh, the capacity constraint. Capacity constraint is here, that the amount of flow on an edge has to fall in between 0 and the capacity it's defined to be. So, like I said, you can peruse this on your own time if you want to, but if we run this, it tells us what the flow is along each edge, which, you can look at that if you want, but it's essentially that's just a graph from before. It gives you the same result. So, just another example of a new problem you can solve with LP. Questions on max flow?
You said it's like can be solved in polynomial time, right?
Mhm.
These are not hard problems, right?
You tell me. Was the exercise hard?
No, in terms of you said that the reason we used the stable matching problem, why we encoded that in statistics to beat the stable matching problem, that could become a
Mhm.
more difficult problem.
Mhm.
But for the max flows, for example, if you solve it directly in polynomial time, or you solve it through linear programming in polynomial time, is there anything more that the linear programming allows you to do?
I mean, I can't think of any deviations off the top of my head that would make it NP complete, but I'm sure there are deviations that you can make. So it's just
But if it makes it NP complete, you can't solve it with the linear programming.
yeah, you can't. Okay, yeah, you can. Yes, you're correct. I don't know the point I'm trying to make here, but it's just a reformulation of it. Forgot what I was going to say. I'll remember in a minute. So, okay, before we move on, some of the assumptions about LP that we kind of made or, just thought of on our own. There are a bunch, but two key ones to highlight. First is proportionality. That the contribution of any decision variable to the objective function is proportional to its value. I think you kind of picked up on this on the exercise that okay, as I increase the amount of rice I choose, my price increases or decreases by the same amount. That's just a result of having linear functions. But most importantly, divisibility. In the problem, I said real value solutions are acceptable. You can buy a real value amount of whatever. Maybe that's not always the case. So this gives way into integer linear programming, ILP. This is essentially the exact same thing as a linear program, where we have our variables, we have our objective function, we have our constraints. Just one additional constraint now, being that all of my variables have to be integer amounts. Now, a question might be why would you ever want to consider this? And an answer to this could be, well, in your problem, you were buying kilograms of rice. If I changed it to bags of rice, no one's going into a supermarket and saying, yo, I want 2.7 bags of couscous. That doesn't happen. So, lots of real-world applications where you're buying or doing integer amounts of stuff. So that's kind of the motivation. So, in a sense, ILP might feel easier than LP, but also maybe harder in the same way. Because with ILP, or rather, before with LP, we can construct our feasible region, and we said, okay, any point within this region could be a solution. And ignoring the trick of looking at a corner, that seems pretty daunting, testing out all of these points. Whereas with ILP, our feasible region can still be constructed, but now our point has to have integer coordinates. So that should be a lot less points to try out. So maybe it feels easier, but then when we have the corner solution, maybe things feel harder. So I don't know, just kind of vibes. This is an example of an ILP formulation. We can read this question. There's We have $45 to buy pies and cakes. We're going to resell them because that's all we ever care to do, to make some profit. But we can only carry 6 items in total. And so obviously, we can't buy fractions of pies and cakes. Actually, that's a pretty bad idea, because you can buy fractions of cakes. Maybe I should have changed this to something else. Whatever. You're buying whole units of pies and cakes, and the formulation looks exactly the same, right? We're maximizing the profit function. We have these constraints. Just our new constraint is they're integers, so it looks identical. So one idea is to say, hey, ILP is pretty similar to LP. They're essentially the same thing, just with this integer constraint. And we have a solver for LP. So why don't we just use it? And one idea would be, take your problem, shove it into an LP, see what solution it gives out, and then maybe find the closest point within our feasible region that has integer coordinates as our potential solution. It turns out this doesn't work. So this is like this part right here, everything that comes on the left side, that's like the feasible region for the pies problem. Our LP solution gives this corner as the solution. If you were to follow this idea of rounding to the nearest point within with integer coordinates, you get 34, but the correct solution is up here with 40. So this idea of just using our LP and kind of rounding, unfortunately, doesn't work for 2 reasons. First reason is we can kind of construct ILPs whose rounded LP solution is arbitrarily far away. So you can think of this as like, if I choose to do this rounding idea, my solution will become as bad as possible. And sometimes there are things we can do to round in a clever way. This is talked about extensively in CIS1921, randomized algorithm. So if you want to take that course to learn more about it, go for it. But you'll actually prove this claim right here. So that's bad news number 1. The more important bad news, it's NP complete. So can't just go ahead and use our LP solver. The good news is it's a pretty hard problem. It's a pretty practical problem because it appears everywhere. So lots of hard work has gone into building solvers to solve ILPs.
That makes no intuitive sense.
I know, right? What part about it is least confusing or most confusing?
Face value, ILP would seem like an easier problem than
Yeah, like ignoring the corner solution that we came up with, ILP seems like much less things to try out, right? But no, LP is actually easier. There's also mixed integer programming, which I will call MIP. I don't know if anyone else calls it MIP, but I like the sound of MIP, so I'm saying MIP. This is just saying some variables can be constrained to be integers, others may not be. So it's in between LP and ILP. ILP said everything had to be integers. This is saying some things have to be integers. So we might talk about MIP as like a generalized version of ILP because it is pretty much the same thing. Yeah, using MIP in OR tools is essentially the same thing as before. So like, we're doing the same import. It's just now our solver looks a little bit different. We're importing this CVC, mixed integer programming. CVC stands for, as it says here, coin OR branch and cut solver. Branch and cut is like the method that it uses to solve these problems. We'll talk more about that next week, next class. We'll actually look at this method and see how it works. But for now, that's pretty much all you need to know. And defining variables is pretty simple. We saw numVar from earlier, a number between 0 and infinity. We can also say intVar, an integer between 0 and infinity. So pretty similar to glop that we saw before.
Is this also NP complete?
Yes. Yeah. ILP is NP complete. Okay. Let's see. Okay, fine. Let's talk about this problem briefly. This is called the capital budgeting problem. And here's how it works. There are n possible investments. You can think about this as like jobs or tasks, like building a school or like, I don't know, cutting down trees. And each has some sort of associated value, maybe like utility or happiness. We also have resources, trees or like machines, tractors, with a certain amount. So maybe 4 trees or 7 tractors, something like that. We also have a cost associated with each investment. So if I choose the ith investment, like the ith job, and that has some resources, well, it's going to cost a certain amount of units of that resources. So maybe cutting down trees, maybe I shouldn't be talking about cutting down trees. Maybe building a school requires like 7 trees for their wood. Oh, that's still cutting down trees. Maybe it requires 1,000 bricks, right? So, and it also requires like 7 gallons of water to, I don't know, hydrate the people. So investments have costs of resources. And we want to maximize our values. We want to choose our investments in such a way that, you know, we're maximizing the utility, the happiness, but still we need to make sure we don't exceed the amount of resources that we're using. So it's a very, like, there's a lot of complexity to this problem, but, you know, just think about it as like choosing to do certain things or not. So I'm more or less just going to give the instance of MIP, but I'll explain it along the way. So first we define our variables, as we always have been doing. And like we would ask ourselves, what is changing? What has the ability to change? And in this case, it's like whether or not we choose certain investments. Like either I choose the ith investment or I don't. So that would be these Boolean variables here, where they're either 0 or 1. They're indicators indicating if I've picked that investment. Then we define the objective function. We're looking to maximize the value. And that's exactly what this summation gives me right here. For each investment that I choose, I'm going to add its value. So for each investment, if I don't select that investment, then xi is 0. So this term isn't contributing anything. But if I do select it, then I want to add its value. So that value would, xi would be 1. So we would be adding the value vi. That's a linear function, so we're good. The constraint is that we don't want to exceed the amount of resources that we have available to us. So for each resource, which we'll call j, we had some amount, a sub j of it, and the amount that we use shouldn't exceed it. So again, we're going through all investments. If we choose the investment, we will add its cost, because xi will be 1. If we don't choose the investment, we won't add its cost, because xi equals 0. The sum of all of those costs should not exceed the amount. Questions on that? Good, okay. So that was like the basic instance of the problem. But of course, like, not all problems might look like that. We might have more constraints to abide by. So let's just consider these possible constraints that someone might say. Like, in order to invest in investment I, we have to have invested in J. So in order for me to have decided to build the school, I must have also decided to build some wells to collect some water. How could we encode this as a linear constraint? Or maybe an easier question is like, what combination of xi, xj would be acceptable?
Well, one thing I was thinking is that like
and xj are 0, 1, right?
Yes.
So, like, the only one that's not acceptable is xi being 0 and xj being 1. It's just like p implies q, right? Like I implies j.
Yeah, let's just write out all combinations and see which ones are good or not. Yes, and I need to voice this to myself as well. Xi equals 1, xj equals 1. So the first one is saying I didn't invest in I and I didn't invest in j, so that's fine, I can do that. This one is saying I invested in j, but I did not invest in I. That's not okay. Or is it okay? No?
First one is okay, right?
First one's okay. The second one?
Second one is not okay.
Not okay.
Everything else is okay.
Wait, am I reading this right? We need to invest in I in order to invest in j. Yes, okay. Yeah, I was thinking about it backwards. Correct.
Everything else is okay.
Everything else is okay, because here we just didn't decide to make j, and here we did. Cool. That's just sort of like truth tabling it. That's not really a constraint just yet, because it has to be like a linear expression. Does anyone know of a way we can make this a linear constraint with an inequality sign?
To make
This?
like a coefficient. I feel like if you make that a coefficient for like xi negative and then xj positive, then like you require it to be less than or equal to 0.
Mm-hmm.
Would that work?
Maybe.
Because then if you put it both together, then it will be less than or equal to 0, and if you put just I by itself, it will also be less than or equal to 0.
Wait, so explain the idea again?
So like xi, negative xi minus xj, or plus xj, I should say, is less than or equal to 0.
So that's just xi greater than equal to xj.
Yeah.
Yeah, these two are the same thing. Yep. Perfect.
Xi plus 1 minus xj greater than 0.
Xi plus 1 minus xj
Greater than 0.
greater than or equal to what?
Just greater than 0.
Oh, greater than 0. Let's see.
It's the same thing, you're adding 1 to that inequality on the right. But you already
Yep.
know. I think the above one is
We can reformulate it. Yeah. Okay. So all of these work. The one I have on the slide is just that. So there you go. That's how you would encode that constraint. Here's another, thing that could happen. Investments I, j, and k are conflicting investments, meaning I can't have any, I can't have I and j, or I can't have all three of them. This might give it away, but I can have at most one of them.
I mean, you could also just say that xi plus xj plus xk cannot be equal to 3, because not equal was one of the things from the right on the slide.
Yeah.
I don't know if you can do it within the Python program, but
Yeah, I think you're close. Just the only other thing is it's poorly worded, but we also can't have two of them.
Oh.
So we would also
Oh, you can have
can't be
just
2
one.
or
Oh.
3.
I thought it was just all 3. Okay.
Yeah, no, it's just poorly worded. But this is pretty much getting at the same thing. That when you sum the 3 together, the only way this is satisfied is if 1 or 0 of them are equal to 1. So more constraints that could appear, and that's how you would solve them. Okay. Let me think about this. All right, I'll let you guys off the hook. All right, we'll talk about this quickly, and then, I know people want to go home because it's been a long day. So we'll talk about this very quickly. Here's another type of problem. We have n jobs that must be completed. We have m CPUs, where m is larger than n, to do the jobs. And, it says each CPU can do at most one job. So either it gets something or it's idle. There's a cost associated with running a job on a CPU. So job J given to CPU C will have some associated cost. And of course we want to minimize cost. So how do we assign things? That's essentially the question. We go ahead and define our variables as we have been doing. again, we are using like an indicator thing. This idea of indicators is very helpful like in the world of modeling. So like these variables will appear a lot. And it's simply like 1 if the CPU C gets job J, 0 otherwise. So we have a lot of different variables, but they're either 1 or 0. So not too bad. And this is what the code looks like. Again, this file will be available to you, but just looking at it, looping through all of the CPUs, looping through all of the jobs, creating a variable xcj. It's an integer variable between 0 and 1 inclusive, so that's essentially like an indicator variable. Now we have our constraints. Each CPU gets at most 1 job. That was part of the question. Mathematically, for each CPU, we'll consider all of the jobs, sum together the indicators for that CPU. That should be at most 1. Because this is 1 if CPU C gets job J. Yeah.
Do you also put the constraint greater than equal to 0, although like it's technically not possible to break that constraint, right?
Wait, I want to make sure I'm understanding. What should be greater than or equal to 0?
X, C, comma, J.
X, C, comma, J.
Sum of X, C, comma, J for all jobs, like the same thing.
Okay, yeah. You could, but since we've defined our variables as 0, 1,
So
you
you
don't
can
need to
ignore
do
it.
that. Yeah, because it'll always be greater than or equal to 0. In code, looks like that. Just doing exactly the same. Hmm?
Can you go back to the code? I don't know if you can use sum like that.
Yeah, me neither. But I'm not good at Python, so that's why. Pretty helpful. There's also this other like phantom constraint that we might have forgot about, but it's also very important that each job gets exactly 1 CPU. Because without this constraint, in theory, we could have given a job to multiple CPUs when that's not really what we wanted. So the motive for this is like for a job J star, once we consider all of the CPUs, exactly one of those things has to equal 1. Because all of the jobs have to be assigned to something. And so the way we can formulate that is take the sum of these variables, and that sum should be equal to exactly 1, and that's exactly what's going on there. So that's the constraint. Okay, that's it. Pretty anticlimactic there, like surprising ending. So yeah, we're going to talk more about linear programming, ILP, MIP in the coming weeks. So like I said, we'll see some techniques there. Yeah, that's pretty much all I wanted to say. So next week, fall break, no class. We'll come back whenever the next class is. As I said at the start of class, start working on homework 2, make sure things are running smoothly, and then, do it whenever you want, but get started on it early. I think that's pretty much all I have to say. So, yeah, see you guys next time. Enjoy your weekends and break.